Okay, so good afternoon, everybody. I'm Madhab Neupane from University of Central Florida, Orlando. Today, I'm going to talk about photoemission investigation of superconducting and magnetic topological materials. So before I start, I would like to thank organizer for giving me this opportunity. I'm sorry that I could not be there in person. I would like to especially thank Professor Peter for the invitation and giving this opportunity. Okay, so this is the outline of my talk. I will be introducing topological insulator and beyond, means some new phases beyond topological insulator. And then I'll talk about superconducting topological materials, for example, strontium doped bismuth selenide, BIPD, alpha PDBI2. And then I will talk about some magnetic topological materials, especially Kagome magnet. Okay, so let me talk a little bit about topological insulator. So what is the difference between conventional insulator and topological insulator? So in conventional insulator, we have conduction band and valence band. They are separated by band gap. But in topological insulator, we have conduction band, valence band, band gap. But within the band gap, we have this surface state, which have this spin polarized channel within the band gap. So how we can understand this topological insulator with simple band-like picture? So one way of thinking is that, let's say in the atomic limit, so when your lattice constant is infinity, then you have energy level, they are separated by some sort of gap. But if you take a real lattice with the experimental value, you have this kind of band. So conduction band, valence band. In some materials, it may be possible that the bottom of the conduction band goes down, top of the valence band goes up. And if you consider the spin orbit coupling, the band gap may open. And if there is some sort of symmetry, so you have this kind of inverted band gap, and within the band gap, if you have some sort of symmetry, for example, time reversal symmetry, you may have this kind of linearly dispersive spin polarized surface state. Okay, so for experimentally, so how you can determine the topological insulator? So I call this experimental checklist. So let me explain what is this. So this is energy versus momentum. So it's kind of dispersion map. This is what we got if we do angle resolved photoemission spectroscopy. So 0 means Fermi level, and x-axis is momentum, y-axis is your binding energy. And when you get this kind of image using the spectroscopic technique, so you will be looking for Dirac point. So Dirac point is basically the points when you see this left moving branch and right moving branch, they cross some point or crossing point. And another thing we are looking for is band gap. So it's basically bottom of the conduction band and top of the valence band. So how big is the band gap? So typical topological insulator, something like bismuth selenide, it has band gap of around 300 milli-electron volt. So enclosing Kramer's point, the state enclosing Kramer's point. So you actually map out the whole billion zone and try to find out how many states you have in the billion zone. That includes the Kramer's point. So another important point, this kind of hallmark of topological insulator is spin momentum locking. So you measure the spin on one side and you measure the spin on another side. So they kind of have opposite spin. So at K, if you have up spin, so at minus K, you have a down spin. So another thing is like number of Dirac cone, like either it's odd or even. So based on that, you have weak TI or strong TI. Okay, so that's all about the introduction of topological insulator. So now let me go beyond the topological insulator. So after the discovery of topological insulator, people started to look for other phases protected by some other symmetry. For example, this mirror symmetry protected state called topological crystalline insulator. Or people also started to look for the bulk state. Okay, so like metallics, like Dirac, Weyl, and nodal-line semimetal. okay, where the spin orbit coupling does not open a full band gap. So there's a certain point of the billion zone, you have conduction band and valence band, they touch each other. Or some sort of interaction. So like, especially like SMB6 type of material, so where you have D and F electron, they hybridize and open up a gap, and there's some sort of symmetry coming the surface state. Or the main focus of this talk is this topological superconductor or magnetic TI. So topological, you can do the proximity induce, or you try to find the intrinsic topological material, or same thing for the magnetic topological materials. Or you can also do some sort of phase transition going from trivial to topological insulator by tuning the spin orbit coupling. Okay, so I happen to work on these various phases, but this talk I'm mostly focusing on topological superconductor and magnetic topological materials. Okay, so let's start with superconducting topological materials. So the motivations come from earlier work from Professor Kaba group at Princeton, where they reported this copper doped bismuth selenide superconduct. So for example, you can see this magnetization and resistivity measurement in this particular copper doping. You see TC is 1.8 Kelvin, in another doping like 3.8 Kelvin. So this actually really started looking for the superconductivity in topological material with doping. Okay, so it's basically search for the bulk topological superconductor. So it's basically copper is intercalated between this quantum layer of bismuth selenide. And another way to introduce superconductivity is just use the pressures. For example, this pressure-induced superconductivity in bismuth telluride. And you can see within 3 to 6 gigapascal, you have TCs of 3 Kelvin. Okay, so one is the doping, another is the pressure-induced. So there's another way to introduce the superconductivity. So this is kind of proximity-induced superconductivity. So this is one of our earlier work, where what we did is we grow bismuth selenide on top of niobium diselenide using MB. And due to the proximity effect, actually, this kind of superconductivity actually can be observed on this bismuth selenide film. So for example, this 4QL, like 4 quantum layer, which is around 4 nanometer, and you can actually, we have a momentum resolution, so you can actually do the temperature dependent measurement, particularly selecting either surface or bulk, and you can clearly see this kind of superconducting gap, this quasi-particle gap, and they actually vanishes if you go above the superconducting transition temperature. If you go above 7 Kelvin or 12 Kelvin, there's no gap, but if you come down, you can clearly see this kind of superconducting gap. Okay, so what we did is, okay, so copper doped bismuth selenide at that time is basically the superconducting volume fraction is not good. So if you see that is in some of the cases, you see it doesn't even come to the 0. So at that time we thought, okay, let's do the strontium doping on bismuth selenide. Okay, so we did like 6% of strontium doping on bismuth selenide, and you can clearly see very sharp superconducting transition temperature with TC is around 2.5 Kelvin, and this shielding volume fraction is at large as 90%. So other group also reported even more than that. So you can see that with the varying doping, the TC can reach close to the 3 Kelvin as reported by other group. Okay, so what we did on this strontium doped bismuth selenide, so we use a spectroscopic technique. So it's kind of a R-pace and time resolve R-pace. So R-pace is basically photon in electron out process. So using the conservation of energy and momentum, you can actually map out the band structure, Fermi surface, electronic structure, and so on. So time resolve R-pace, what you do is you use the pump probe setup. So you pump your system, and then your probe actually try to picture what is happening on the unoccupied side, okay, on the excited side. So for example, you can see is in native is highly p-doped. Fermi level is well deep in the bulk valence band. But if you pump it, you can see excited state, surface state, Ball conduction band, but they decay pretty fast. So within 10 picosecond, everything is recombined. So it's a short optical lifetime. Okay, so we did the similar measurement on this 6% strontium doping bismuth selenide. And without pump, what we see is this kind of Dirac state where Dirac point is deep below around 550 MeV below the Fermi level, but there's some sort of this kind of 2D band, 2D quantum Weyl state near the Fermi level. You can see 22 eV, 24 eV. And using this pump probe setup with the 6 eV laser, we can clearly see this kind of Dirac band as well as 2D band. So we pump it and you can see this occupied side and then, a little bit 2D state extended over here. Okay, so, and then we try to understand the relaxation dynamics. So you actually, because we have a momentum resolution, so you sit here and then do the time scan and see what will happen. And this is how we got. So you can see that this right surface state and left surface state, they have one kind of decay mechanism, but this 2D state has a slightly different type of decay mechanism. So both relax within the 5 picosecond. Okay, but seems like it has two different decay mechanism, and obviously there's a short optical lifetime, couple of picosecond. And one important thing is if you are dealing with a metallic sample, it's very hard to pump. I mean, very hard to get the state above the Fermi level. Okay, so then what we did is we tried to fit this surface state and 2D state. Okay, and we found that this 2D state is well fitted if you use two double exponential decay fitting function. But the Dirac right and Dirac left, so they fitted well with a single decay function, single exponential decay function. So we did a little bit of modeling and we come up that, so this topological surface state, mostly the decay mechanism is mostly dominated by intraband scattering, but this 2D state, it has this double decay function. So it has both intra and interband. So if you consider this kind of decay constant, so it has kind of longer decay similar to the surface state, but it has one faster decay, which may be coming from this strontium vibrational mode. Okay, so that's all about the dope system. And then we thought, okay, let's try to find some intrinsic topological superconductor, like not dope. Okay, so the idea is single material with topological surface state and superconductivity. So our idea is to get this topological superconductivity. So it's a source, discovery, and characterization. Okay, so then we come up with this BIPD, we including other group. So this is monoclinic unit cell and non-centrosymmetric structure. You can see that crystal structure here. So this top surface is different than bottom surface. And it has very metallic, and also it has sharp superconducting transition temperature around 3.7 Kelvin. And you can see very sharp core level, and this is a bulk and surface brilliant zone. Okay, and we did this electronic structure measurement, and you can see this energy versus momentum dispersion map. And you can see this kind of cross state, X kind of state. And we did this kind of constant energy contour, and around 700 MeV, you see this dot over there. And if you go higher, you will start to see circle. Okay, and this kind of, we see linearly dispersive state around 700 MeV below the Fermi level. And we did photo energy dependent. So this state always remains there. It doesn't disperse with photon energy. Could be signature of surface state. And we say, okay, it could be some surface originated, some dangling band or something. And what we did is we call this thermal recycling. So we raise the temperature and cool down. So it is up to 300 Kelvin and come back at 20 Kelvin. So it's always there. So it's kind of very robust state. So another thing we did is we measured the spin polarization, and you can see spin at this line. So I mean, this branch is opposite to the spin at this branch. You can see it's going down and up, but here going up and down. So it looks like it's a spin polarized state. Another interesting thing we found on this system, this is non-centrosymmetric. So if you clip one side of the surface, the location of Dirac point is different than if you clip on the another side. So it's a direct observation of non-centrosymmetric electronic structure. So Dirac point is almost around 50 MeV offset. So which is kind of in agreement with the DFT calculation. Okay, so summary for BIPD. So we get presence of surface state in non-centrosymmetric superconductor, presence of surface state about 700 MeV below the Fermi level, spin polarized state, and non-centrosymmetric electronic structure we observe. Okay, then we started to think of some Rasper system which might have superconductivity. Okay, so the motivation is actually comes from this theory paper. So where they say this coupling of S-wave superconductor with Rasper split system in a magnetic field could provide Majorana zero bias mode. So thinking along that line, we come up with this alpha PDBI2. So this is superconduct, so less than 2 Kelvin. And we see some sort of Rasper state near the Fermi level as well as some sort of Dirac state. Okay, so this is a crystal structure and characterization of alpha PDBI2. It's a monoclinic crystal structure, so it's a centrosymmetric. You see top and bottom surface look same. And this is a resistivity measurement. So TC is less than 2 Kelvin. And this is a billion zone, and you can see core level measurement. And this is a unit cell. Okay, and we did the electronic structure measurement, and you can see clearly it's very metallic. There's a lot of band near the Fermi level, but there's some sort of Dirac-like state around 1.2 eV below the Fermi. So if you do Fermi surface map and go to the higher binding energy, you can see those state, how those revolve. Okay, so it's if you do the wider mapping, you can see a lot of pockets, a lot of bands. So it's highly metallic at normal state. Okay, so we did the band structure calculation, and you can see if you include the spin orbit coupling, there's always this kind of Dirac state as well as Rasper state near the Fermi level, in the vicinity of the Fermi level. Okay, so this is how our data looks like. So there's kind of Rasper state at A point, which is in agreement with the DFT calculation. Okay, so conclusion on this superconducting topological materials. So in strontium doped bismuth selenide, we found Dirac state, 2D state. Dirac state is around 450 MeV below the Fermi level. So using pump probe measurement, we found different decay mechanism. And in BIPD, we observed a Dirac state well below the Fermi level. Spin polarized state is a non-centrosymmetric electronic structure. And alpha PDBI2, the Rasper state in the vicinity of Fermi level, Dirac state below the Fermi level, but it has centrosymmetric structure. Okay, so let me go to the magnetic topological materials. So these materials are kind of very hard in condensed matter system right now. So we work a couple of systems. So for example, first is UIN2S2. So this material is theoretically predicted by CDI group to have this higher order topological insulator. So there, what we did is, so it's a magnetic with AFM temperature is around 16 Kelvin. So we measured the electronic structure below and above the transition temperature. Okay, and we clearly found that below the transition temperature, there's some sort of splitting there. You can clearly see these two pocket below the transition temperature, but only one pocket above the transition temperature. And we also study this kind of breathing Kagome, where we see a lot of flat band. I'll describe more this. And also we study this 166 type Kagome system, like ER-MN6SN6 or HO-MN6SN6, where we see very complex magnetic structure. Dirac still looks like a little bit higher than above the chemical potential. Okay, the another system we study this CLSI, cerium-based system, where so it has a magnetic as well as it has non-centrosymmetric. So actually, this system we observe this kind of Weyl point as well as Fermi arc, and this tuning the temperature, you can actually tune the Weyl points. And on this NDSP system, we kind of see Fermi arc and very complex structure below the magnetic transition. This is also AFM with temperature 15 Kelvin. Okay, so let me go a little bit detail on Kagome system. Okay, so why Kagome system? Okay, so Kagome is like a Japanese word, it's kind of bamboo basket. So it's basically corner sharing triangle. So if you have a triangle, so let's say if you want to arrange this antiferromagnetically, and let's say if you arrange your one is spin down, one is spin up into another corner, but at third corner, it doesn't know which way spin has to be pointing. So it created this kind of spin liquid phase, this spin frustration or geometrical frustration. It also has a charge frustration. So let's say electron at here, here, and here, the electronic wave function may go to the destructive interference, and they are kind of localized, and that can give this kind of flat band in your electronic structure. So it has this hexagonal structure, okay? So that hexagonal structure might give you, it's like a graphene, like Dirac state or band of singularity. So the interesting thing in the system is that, let's say, spin doubly degenerate, but if you broke the time reversal symmetry, it can be singly degenerate. And if you use the spin orbit coupling, and you can open up a gap, on that gap, you can see this kind of edge state. So recently using STM in one of the 166 system, Princeton group, Professor Zaid Hassan's group reported edge state on this band gap, Swan gap state, within the Swan gap state. Okay, so we work on breathing Kagome lattice. It's kind of very new. So why breathing Kagome lattice, or what is breathing Kagome lattice? So before that, so let me talk about the motivation. So this motivation actually comes from this 2D community, where they are looking for this layer compound van der Waals transition metal can be exfoliated into the single crystal. 2D ferromagnet is basically looking for a 2D ferromagnet, environmental friendly, biocompatible, non-toxic, stable with environment, semiconductor, and good for light absorption. So thinking along that line, there's a couple of theoretical predictions saying this niobium halide, so niobium chloride, bromide, iodide, monolayer are ferromagnetic. And there's a theory calculation predicting the Curie temperature like 31, 56, 87, but in other group, they are predicting even much higher. Okay, so this work is done in collaboration with Professor Xiaodong Su and Ting Kao of University of Washington, Seattle. Okay, so what is breathing Kagome lattice? So in the Kagome lattice, you have this kind of triangle, but this triangle size is same into the different layer. But in breathing Kagome, the bonding length in alternating triangle of the Kagome geometry are different size. So this triangle size and this triangle size is different. So breathing Kagome lattice could be more interesting because it has this local electric dipole moment, so potential for ferroelectric ordering. So it has gapping of the Dirac point, so potential of higher order topological phases, intrinsic topologically flat band coming from this correlation. So that's why this system is even more interesting. Okay, so then this niobium iodide, niobium-based halide system, this niobium has this kind of breathing Kagome geometry. You can see clearly here. So within the layer, so the center atom is niobium and is sandwiched with iodine. So this is kind of covalent bond, but between the layer or interlayer, they have a weakly van der Waals bonding. You can see it's a rhombohedral space group. So A is around 7 angstrom, but C is around 41. So C is much, much larger. So it's easily exfoliated. So this how you can easily get down into the monolayer. Okay, so we did the electronic structure measurement. So we kind of surprised to see this result. You see energy versus momentum. So there's a lot of flat band there. Very weakly dispersive band. You can see it's a semiconductor, so it has a band gap around 500 milli-electron volt. But you can see clearly a flat band here around 1.2 eV. So we did some sort of analysis, and you can clearly see two peaks here. So there's two band, and there's another broad flat band over here. So we did second derivative measurement to confirm that. And again, we have a flat band over here. Okay, so we did the first principle calculation. So you can clearly see very weakly dispersive band A and B, and there's some sort of flat band on C and D over here, very weakly dispersive band. So to prove that, we did the photo energy dependent measurement, and we clearly see this flat band is some sort of 2D nature. They don't disperse much with the photon energy, but this band around 2 eV below, so this is kind of highly dispersive with the photon energy. So it's mostly originated by 3D. So this is a more photo energy dependent data, which clearly show less dispersive band near the Fermi level, but highly dispersive band around 1.2 eV. Okay, so we also did the polarization dependent measurement, and we found that this linear horizontal, some band is highly enhanced, and the linear vertical polarization, the other band is highly enhanced. So we come up that this band A and B is strong in linear horizontal polarization. The origin is DG square orbital of niobium, and C and D is in linear vertical polarization, which is DXY orbital. So different orbital coupled differently with the polarized light. So this is the calculation, and you can see the band close to the Fermi level, this band A and B and C. So those are basically coming from niobium D orbital. So niobium is actually forming the breathing cagomylides. But this band is basically coming from iodine P, which are mostly the dispersive band. Okay, so we also compare the bulk and monolayer. So you can see the frontier of band looks similar. Well, bulk band has more bands as compared to the monolayer, but you can clearly see this negligible Kg dispersion because C is much, much larger. Okay, so summary for niobium iodide. So we study electronic structure in breathing kagome. So we found the flat and weakly dispersive bands. So bands are sensitive to the polarization of light, and flat and weakly dispersive band originated for breathing kagome layer of niobium atom. Okay, so I would like to thank my collaborators. So especially samples are provided by Professor Kaczorowski Group of Polish Academy of Science and Saudeng Su Group of University of Washington, Seattle. And the calculation mostly done in collaboration with Professor Arun Bansal Group of University of Northeastern University and Professor Openier of Uppsala University of Sweden and Tinkau of University of Washington. So this is my group at UCF Physics Department, and these are my funding agency who are supporting all this interesting research on quantum materials. So with that, thank you for your attention.
Thank you very much. Thank you for this nice overview over so many different materials. Are there questions in the audience? Maybe I can ask a question concerning the the palladium bismuth 2. You very briefly sketched the resistivity, which I think looked linear up to pretty high temperatures. This is always, controversially discussed, or, there are different models and so on. Can you, palladium bismuth 2?
It's just, it's not bismuth 2, it's just bismuth actually. It's a 1-1 system.
No, the 1-2 system.
Oh, the alpha, I see.
Yeah. Yeah, here it is.
Oh, yeah, this
So
one.
that looks very much
Okay,
linear
so
to me. So that's
yeah,
almost,
so
can you comment?
yeah, so it's basically for our measuring temperature, so it looks highly metallic. I mean, if you go up to room temperature. So we try to measure around 20 Kelvin or around the room temperature. So this always very metallic. We see a lot of band over here.
Okay, but you don't want to comment any further on it, on this linear resistivity? I mean, any
No,
correlations
no.
going on or so on? Oh, okay. Are there any other questions? Well, if not, we run a little bit over time. Thank you very much again.
Thank you for the opportunity.